In this video, I'll teach you, in some ways, the most powerful SQL command, and in some ways, the most useless SQL command there is, and that is creating indices. So what is an indice, or singular, what is an index? Well, back in the old days, there was these things called books. I guess I have a couple in my office. And in the back of the book, they would have an index. And this index was basically all of the terms that appeared in the book and what page those terms appeared on. And the most important thing is those terms weren't in any random order. Those terms were ordered alphabetically, so that if I wanted to find which pages mentions cats in this book, well, I can look by just binary search to figure out where is the cats entry in this index and which pages talk about cats. That is what an index is. It's basically a sorted way to find where the content is in your larger database, in your larger table, in your larger document. And so without an index, if I wanted to figure out which pages talk about cats, because I really love cats, I would have to go through each page from beginning to end looking for cats. But with an index, I can instead go to this sorted area in the back, look up where is cats there, really easy operation, and then jump straight to the parts of the book that I actually care about, and I can ignore the rest of the meaningless pages. Okay, the important thing to note is indices have no external effect on a database. Having an index and not having an index would not affect the things that are returned by a select statement. It won't affect your ability to update or delete columns. It won't affect your ability to add or drop tables. None of that will have any effect. And that's what I mean by I say index is kind of the most useless thing. However, the one big effect indices do have is on performance. They can make some queries that might take hours take seconds. And so if you care about performance, and in general, performance is often a very important criteria for a database. It tells you how many servers you have to buy, how many database administrators you have to pay salaries on in order to make your website actually work. And so by default, every table you've ever made is actually indexed. And sometimes SQLite doesn't actually tell you that. It's indexed according to each table's integer primary key. And if a table doesn't have an integer primary key, because not every table has to have one, it actually makes a secret one called row ID on your behalf, because indices are just so useful. All right. And so actually, well, the row ID isn't an index per se, but it is a special column that indices can use and exploit for what they do. And we'll talk about how that works in a little bit. So how do you create an index? Well, once again, this is another example of a DDL, of a data definition language, a way to specify objects in your database that aren't the data themselves. And so you say create index, and you give an index name, on a particular table, and then in parentheses you specify which columns you care about. So if I wanted my cats index, I'd say create index, the index of this book on the book, and the columns that might be looking over might be the words in a particular page or the content of a page. Well, it would make a lot more sense when we're doing real tables instead of my stupid example. Okay. You can also have an index that has multiple columns to sort by. So in the back of books, generally you're just sorting by topics, but you might want to sort by topic and grade level, so that if you want to find, hey, I want to find all of the topics on recursion, and then within the recursion topic, I want to sort not just the 100 pages in the textbook that matter with recursion, but I also want recursion grade level 1, followed by recursion grade level 2 pages, followed by recursion grade level 3 pages. You can have multiple columns to sort your index on. We'll explain exactly when and why you would want indices in a little bit. And of course, if you can create indices, you can also drop them, and there's also the if exists and if not exists, just like before, if you want to use those extra clauses. In general, we won't be dropping indices in this class, because we really won't be working with databases where the indices are all that expensive and what you would have to drop them. All right, so let's back up a little bit. When should you create an index? Well, the primary reason you'd ever create an index is when you need to look up particular rows in a table, but not according to their primary key. Because by default, tables are already sorted according to their primary key. Looking up by their primary key is really easy. If your table is sorted by student ID, finding student ID number 17 is just a quick binary search for student ID 17. But if you need to look up a table by the student's name and it's not sorted by name, then it's a lot more expensive. So an index allows you to quickly get matching rows when you're doing a lookup on particular columns. And so that might sound really great. Why don't I make indices for every column so that all of my queries can be super fast? Well, the big problem is indices are expensive, especially when you need to modify the underlying table. If you ever need to update a particular row or insert new rows or delete rows, you need to adjust every index that points at that table because every index is now slightly wrong and needs to be fixed. So having a table that has a whole bunch of indices on it can make it really fast to do queries, but it makes it very slow to ever change the data there. Another big cost of indices is they're not free memory-wise either. You need to set aside space, like in the book or in your database, to hold the data that says, here is the sorted column and here are all of the rows that each of those columns refer to. So if you have large databases, which really there's no reason to make an index on if you have really large tables, you will also have very large indices. And there's really no point to make indices on small tables because queries on small tables are fast already. Okay, so the rest of this video is content that I cribbed primarily from the SQLite documentation because it's just a really nice way to walk through it. So if you don't like the way that I presented it, feel free to read it for yourself or read, and there's whole books. There's a really great book called Use the Index, Luke, that talks about when indices are useful and how they work. This class really isn't very focused on getting like super high performance out of your database because that will vary based on different databases. And in reality, whenever you're trying to optimize something, there's only so much good you can learn from these sort of big concepts. The big thing that you always learn when you try to optimize anything is you need to do a lot of profiling and really just profile, try something to see if that makes it faster. But I'm going to be talking about circumstances where indices are almost always useful, and you'll be able to recognize these and use indices if you have to write database software of your own. Okay, so to start with, I want to make it really clear that SQL is what's called a declarative language. Right now, almost all the languages you've ever learned are procedural languages, where you basically instruct the computer, do this step, then this step, then this step. SQL, it doesn't work that way. In SQL, you specify, I want the answer to this question. How you do it is up to you. And it's the job of the SQL implementation to take your declaration, give me all of the rows ordered by name, and to figure out what are the steps that it needs to do underneath, what are the steps that it needs to do itself to generate that answer. And different implementations may solve it in different ways, and it is most of the time the implementation does it much smarter than you ever could. It's like the compiler. In general, its results are much better than anything you might try to do by hand, but sometimes you can help this by making indices. SQL won't by default make indices to respond to queries because they're just really expensive some of the time. But if you know this is a query that is very slow and you need to make it faster, making indices can help. So let's look at some example indices and the sorts of queries that they facilitate. So here is this somewhat fun database. It's called, or fun table called Fruits for Sale. Okay, so this table has 3 columns, fruit, state, and price. And it looks like it has 4 because there's this secret hidden column called row ID that the SQLite made on my behalf because I didn't actually specify an integer primary key as any of my particular columns. So it made one for me, and it's called row ID. And this table is always sorted according to the integer primary key, which in this case is row ID, and it's marked in green just to show that it's not a real column from the database, but it is there. And so then I used a bunch of insert entries to fill the data, say the data here. And so once again, what is that 4th column, that row ID column? It's because we didn't specify an integer primary key. It made this row ID column for me. Tables are always sorted according to their integer primary key. Okay, so let's imagine a sort of simple query. I want to select the price from the table Fruits for Sale where the fruit is equal to peach. So how would we do this? If I handed you this table, if you had to do it by hand, how would you find the columns, how would you find the prices of all of the peaches? Well, Without an index, and this is again by default, we have to do what's called a full table scan. We have to go through every row in the table and check, are you a peach? Are you a peach? Are you a peach? Yes, you're a peach. Report your price. Now keep going. Are you a peach? Are you a peach? All the way to the end. And there's no way to do it any faster because you don't know which rows are peaches until you check each one. And so this is really slow if you have a huge table. Now, obviously, for a table as small as this, it's not slow. But if you have a table that has thousands or millions of rows, and many of the databases that you guys will be working with will, this is very expensive. How expensive? Well, multiple choice question time. What is the big O notation for a simple select statement like the one that we had before? All right, this should be a pretty easy question. The answer here is n. You have to go through n rows, so it takes n time. If big O notation is something that you're not comfortable with, then I strongly recommend refreshing it because it will be topics like that that we're going to be covering on the exam and so forth. I'm expecting you to know this information. If not, this is something that you want to quickly revisit, read a tutorial. I'm not doing advanced stuff with Big O, but understanding these sorts of performance implication for indices is something that you guys will be expected to know. Okay, so that's how we work without an index. Let's create an index. How would you write that? You'd say create index, fruit index on, fruits for sale on. Now what column? So let's say we do it on the column fruit, because that's really the column that we cared about in our previous query. We cared about finding the peaches in the fruits column, so let's make an index on that. And so what does that index look like? Well, it looks like a little mini table. It has the column fruit, and it always has the integer primary key. And note that this little table is ordered by fruit. Apple is first, strawberry is last. They're all alphabetically ordered. So now when I want to find a particular fruit, I can just do binary search on this fruits column, and I can find all of the row IDs that correspond to those fruit. So how would my previous query from before go? Well, I have my fruits index, so I'm trying to find, I need to find the columns that have a fruit equal to peach. So I look in my fruits index and I say, hey, the columns where fruit is equal to peach is row ID 4. And so then I go to fruits for sale and I do a binary search for row ID 4, because once again, this table is organized by row ID. Oh, there it is. And what is its price? 60 cents. That is what I report. 60 cents is my one row that matches peach. So once again, just to repeat, I do a binary search on the fruits index for peach, determine what the row ID is. Then I do a binary search in fruits for sale to find the row ID that I'm trying to look up, and I can return that price. So if you have an index into fruit, what's the big O notation? All right, this one, a little bit trickier. You might say, well, I need to do a log n lookup in my index, and then I need to do a log n index in my, or log n lookup in my table. So that's log n plus log n. But of course, if this isn't really obvious, log n plus log n is really the same thing as just log n. Once again, big O notation. Refresh it if you're not comfortable with it. So the correct answer here is 2. It's log of n, because I do a binary search and then another binary search, which is really the same performance as just doing a binary search with a constant, or not with a constant, but with a fixed magnitude. Okay, using lookups on indices also work if there are multiple rows that match. So for instance, if I want to get all of the prices for the oranges, I do the same sorts of steps. I do a binary search for orange in my fruit index, find the row ID, do a binary search in my fruits for sale, return the price, and then I go back to the fruit index and say, hey, by the way, are there any more oranges? Oh, there happens to be another orange. Do another binary search in the table, report that price, and go back, are there any more oranges? And once there are no more oranges, I've returned all of the rows that I need to return. So an index is useful even if you're doing a lookup for more than just one row in the table. Okay, so that's great. But what happens if we have more complicated queries? What happens if, you know what, I want to return the prices for all the oranges that are sold in California? How would I do that? Well, I can still use my fruit index. It makes it really easy for me to find all of the oranges. I do the same process of look up oranges, look up in my fruits for sale, report the prices, with the extra caveat that I need to check before I return that you are actually in the state of California. So the first time I go through, I find, oh, I have an orange in row ID 1. oh, I can't report it, you're from Florida. And then I do, oh, I have an orange in variety 23. Hey, 23 is sold in California. I report $1.05. All right, so the index facilitates other queries, even ones that use other criteria to select rows on. However, what we could do to speed things up, if we make another index, an index here called state index, which represents the an index on the states that are mentioned in each row. And so we could actually go to our previous query, and instead of using the query for fruit, the index on fruits, we can use the index on state and say, hey, find me all of the rows that are sold in California, and then I can go and look those up, and instead of, and before I report, I just need to make sure, oh, by the way, make sure your fruit is orange as well. And so, the first one is I look up California 5, and I was like, oh, no, that's a grape, don't report it. And then I look up, oh, there's another thing that's sold in California, it's in row 23, and that happens to be an orange, that is what I report. Now, once again, indices never change the result from the outcome. We're always returning the same rows, but by having a fruit index or a state index, things can go a lot faster. Okay, so index conclusion. If you have multiple indices that you can choose, for instance, in the previous example, we could have used the index on fruit, or we could have used the index on states. Which one is better? And so this is actually a lot harder of a question than what it seems. So first off, let's go through these answers. The index was the most rows. Now this is clearly wrong. Every index has as many rows as the original table. If your index doesn't have as many rows as the original table, something has gone horribly wrong. So that doesn't make any sense. The index with the least duplicates. Now this one could be right. We'll have to come back to that. The next one, the index that is sorted. Well, that's also kind of a stupid thing to say. Every index is sorted according to something. So then we go back to the index with the least duplicates. Now this is useful because if your index has very few duplicates and you're looking for just a particular value in that index, that's really great. However, it really depends. Depends is actually the correct answer here. So you want the index that will basically limit the number of rows that you have to check in further steps as much as possible. You want an index that can constrain the outcome. So if you have, you're looking for all of the oranges sold in California, you have an index on fruit and you have an index on states. If you have a whole bunch of fruit sold from California, using the index based on California or based on states won't really help you much because it won't really limit your options very much. You're still having to look through a bunch of rows. But if you have a whole bunch of different types of fruit being sold and not many oranges, you really should use the fruits index to limit the number of rows. You only have to consider a couple rows in the big table, which oftentimes corresponds to the index with the least duplicates, but it really depends on your query. And so which index is best is usually something that the SQL implementation tries to be really smart about, and it's actually a really hard question to actually have solved. And it's beyond the scope of our class, beyond try to pick an index that doesn't have a lot of duplication. So it can find particular rows more effectively. Okay, with that, there's a better way than having to choose between the index on fruit or the index on states. Why don't we make an index that has both of them? So here I've made an index that has multiple columns. It has both the fruit column and the state column. And the way that this works is you sort according to the first column, so in this case, fruit, and then where there are ties, you break that according to subsequent columns, like the state column here. And so how is this useful? Well, back in our previous question, how do I find the tables that are oranges from California? Well, I look in this index for the orange, and then I look for the ones in California, and they'll all be right next to each other because they'll all be sorted right together. And so I can just immediately go, 23 is the one row that is both an orange and from California. That's the one row I need to return. I don't need to do any checking of other rows because that's the only possibility there is. And that's really useful. And heck, this fruit state index is useful even for the simple query. If I want to find all of the peaches, I just look in this fruit state index, find all the peaches, and this time I just don't even bother looking at the state, just return all of the peaches. This fruit state index is actually just as useful as the fruit index was before. And so you don't have to use every column in an index if it's not needed for a particular query. Okay, so you might be going, gosh, fruit state index was so useful. Why don't we make an index of everything? And in fact, sometimes that is useful. So I'm creating an index that includes all of the columns in fruits for sale. This is called a covering index. It has all of the columns used in a given select statement, including the output. So what would that look like? So let's look at our previous query, find all the oranges in California. I can say, okay, finding all the oranges in California is really easy because they're sorted by fruit and then state, and then I have my price right there. And note, I don't actually have to do a lookup in my other table anymore. Why? Because I have the price right there. I can just report 105. Because if my queries are always specifying fruit and states, the price I care about is right there in this index itself. I don't have to do the second binary lookup. So if you have a covering index, what is the big O notation for lookup? Yeah, so the answer here is log n again. You still have to do log n to figure out which rows you need to return. And so you might be going, gosh, you spent all of that work coming up with a covering index instead of just a normal index, and you only got it to log n time. Well, the nice thing is that that covering index is log n time, whereas some of the other ones, the ones with multiple criteria, would be log n plus n, because you would have to check the sometimes many rows that could be returned, and log n plus n is actually n. So if you have a covering index for a given query, you can guarantee that the lookup is log n. And so the important thing is you tend to want to have covering indexes. You want to have all of the columns mentioned in a query sorted so that instead of having to look at your actual table, you can just look the things up in the index and not have to do the second lookup. You don't have to do any checking which rows need fulfill the other columns that aren't part of your index. Okay, so we've been talking a lot about AND operators. I want the oranges, the fruit that are oranges in the state that is California. I want an orange and California. What if I care about the rows where they're either fruit or they're from the state of California? Let's say I really love oranges and I also love the state of California and I want things that are from both. So how do you do that? Well, you could do a full lookup and check each row, but we're smarter than that now. We know about indices. If you have an index on fruit and you have an index on state, it's very easy to find all of the orange rows, and it's very easy to find all of the California rows. And then if you do a union operation so that you remove duplicates, like in this case, row 23 is both of them. So you do the union to just figure out, okay, what are all the rows that fulfill one or the other criteria? And then you can do the binary lookup. Find row 1, find row 5, find row 23. And those are all of the rows that correspond to either oranges or from California. And this is called the OR by union technique. So if you had to implement this yourself, you would need some sort of union operator here to make things work, and you do this lookup. And there are ways that SQLite can make this lookup a lot more efficient by kind of doing special caching and things like that, which are beyond the scope of this course. Okay, so now we spend a lot of time determining which rows to return. But another useful thing that indices can provide is sorting. So for instance, let's say I want all of the rows in the table, but I want to order by fruit. I want the apples to be at the top. So how would you do that? Well, the way that you'd have to do that is you take this entire table and you pass it into some sorter function that shuffles all of the data around for the output purposes. And this sorter is often quite expensive, especially if you're working with millions of rows and large data sets. So sorting is an expensive thing to do. And if you have to sort your entire table for every time that you have a select statement, that can be very expensive. So because we don't have an index, we have to sort everything together. And so what is the big O notation for sorting without an index? And now, if you don't know just immediately, what is the big O notation for sorting a list? You probably shouldn't be in this class. It is n log n. All right. So what do we do if we want to order by row ID? Okay. If you need to order by row ID, you're like, hey, you know what? I don't need to do any sorting at all. Everything is already sorted beautifully. All I need to do is just output each row. right? Output row 1, then 2, and 3, just work your way down. It's already sorted by row ID. And if somebody wrote select star from fruit for sale, order by row ID descending, how would you do that? That's not any harder. You just start at the bottom and work your way to the top. That's really easy. You don't have to do any new operations. You don't have to do any calculations. You just output the data in a different order. Okay, the harder case is, okay, well, let's go back to our previous thing. We want to order by fruit. But heck, if we have a fruits index, we've already sorted by fruit. We know the first thing we need to return is row ID 2, and then the next thing we need to return row ID 5. And so we can just go through our index and do binary lookup on the fruits for sale to figure out what we need to return. All right, so with an index, what is the big O notation for sorting with an index? The answer here is n log n. What does that mean? Well, you have to go through each row in the index, so that's n, and you have to do a binary lookup for each one to figure out the associated row. That's log n, so you have to multiply those together. And you might be going, Josh, I thought you would save us time by having an index. And I didn't actually say that. Well, actually, I kind of did. So having an index means it's still n log n time, but it's actually a faster n log n than before. The previous one, you had to take all of your data and basically copy it into some place that can do all of this fancy sorting on your behalf. And that takes up memory and that takes up space. Whereas with n log n, you can do everything in place without having to move any data around, and so that actually makes the operation considerably faster. So even though it's still n log n, it is much faster because you don't have to do as many of the memory operations because you're just doing lookups in existing data structures. Alright, so let's look up another slightly more complicated example. What happens if we want to limit the rows we return by having a where clause to filter out many of the rows, and we want to order by state? So how do we do that? Well, the most efficient way to do that is if we have that fruit state index from before, we can easily find which are the rows we care about. Those are the fruits that are oranges. And you know what? Heck, this index is already ordered by state. As long as we just only look up the rows that are oranges, we can just do a nice binary lookup for the columns that we need to return. And so this means that we only need to sort a very small subset, or really we only need to do binary lookups for a very small subset of the data. Whereas if you didn't have these indices, you would have to order everything and then figure out what are all of the fruit that need to be returned. This is, once again, another way to save time. So if you are combining both sorting with an order by and filtering, using the appropriate index can save you a huge amount of time. Because what it does is, all it does is it limits the rows that we care about to those which are oranges, the leftmost column in the index, and then outputting the price for each record by state because they're already ordered by the index. However, the even faster way to make this work is if you have a covering index. So if we had a covering index here, which is fruit, state, price index, well, we can find the fruit that we care about, the oranges, they're all right next to each other, right in the middle. And they're already ordered by state. And what is the data we need to return? Just those rows themselves. There's no need to do any appropriate lookup as well. So actually, if you have a covering index, it makes a lot of queries extremely fast. Because here, there's not even that binary lookup at another table. You have all of the data that you want. You can return it as you see it right here. So the important take-home message from all of this is having the appropriate index can make both filtering and can make collating or ordering those things much, much more efficient than if you have to process all of the rows in the table for every query that you need to perform on it.